So let's see. Let's go through now 2D. All right, so we've got 1D. You're going to have some practice with that. Or you had some practice with that. 2D. The homework that you're going to be doing is a 2D solution. And I guess I could give you a 1D and a 2D, but I'm not that mean. So we'll just skip to the 2D one. So what are we trying to do in 2D? Well, in many problems, we can't actually come up with an analytical solution. Just as with 1D, maybe there's something complicated going on. We can't really come up with a good way to solve the problem analytically. So our resort is to go to numerical solutions. The computational expense of this is pretty high. So pretty quickly you run into like intractable problems if you're not careful about the number of nodes that you choose. But this is a very, very flexible technique. So I want to walk through, like, it's basically the same process, 1D and 2D. In fact, almost identical. There's just more that you have to do for 2D. All right. So what's motivating this? I guess let's look at an example where we can kind of get to the ODE or the PDE, and then we'll sort of stop at that point. So all right. So the analytical basis for 2D models is Fourier's law, right? The analytical basis is still Fourier's law. We're still governed by Fourier's law. So let's write that out in 3 dimensions here. So Fourier's law is q dot double prime is equal to minus k times the gradient on temperature. All right, so this for us is minus k times partial of temperature with respect to x. So let's do this in like vector format. So we have this partial t with respect to x times the I vector, so I hat, plus partial t with respect to y and the j hat, plus partial t with respect to z and the k hat. Right, k hat is different from conductivity k. So we have this, let's say we've got this like basically 2D problem where there's really no change with temperature in the z direction. Then this just simplifies down to, the first 2 terms. All right, so this is, I guess, the analytical basis. Let's actually go through and look at how the formulation works. So when would this be relevant, I guess? Let's imagine we have an extended surface, or fin. It's not an extended surface, but it has some temperature profile. Right? So that temperature profile might look like this, right? Where there's some temperature profile both in x and in y. Right? This is x, this is y. Sorry, my drawing is a little rough there, but basically you have some temperature, and it's changing both in the y direction and in the x direction. So if the temperature profile looked like that, and it had this really significant gradient, it's really not fair to model that as an extended surface, right? Because extended surface is saying, well, as a function of y, I'm basically uniform. In this case, let's say that's not valid. So our BO number is much larger than 0.1. Let's say it's 1 or something like that. So, okay, we decide that we can't justify this. We have to go to a 2D model. If we were to try to tackle this analytically, how would that look? Well, we'd take our control volume. So let's say we have some control volume here that we just kind of pick out. That control volume is not spanning the entire height, because if it did, then we couldn't model any gradient in y. We want to model both in y, so there's a differential height in y, and in x, differential length in x. So let's blow that up over here as I've done, this dotted line, and do the heat flow analysis. So this is internal. We've got coming in q dot x, leaving we have q dot at x plus dx. All right, so this, I guess we could draw like this. This width here is dx. But because we have this gradient in the y as well, we also potentially have heat flow in y. So let's draw it like this. This is q dot y. This is q dot y plus dy. Right, so this distance here is dy. So a differential element has differential thickness in x and in y. And now our job is to figure out some governing equation that lets us solve this problem. So we'll just take it like one more step, and then you'll see it's kind of hopeless. Except for numerical solutions, right? That'll help us. All right, so we're going to do the energy balance. That's in plus generated equals out plus stored. Coming in, we have q dot x. We also have q dot y now, right? This is different. So q dot x plus q dot y are both coming in. Leaving, we have q dot at x plus dx plus q dot at y plus dy. All right, so this process is conduction, so it's modeled by Fourier's law. We need to then go in and expand out and then substitute our rate equation in. So first we can expand things out. Let's do that here. So this term here becomes q dot x plus partial q dot x with respect to x times dx. This term here becomes q dot y plus partial q dot y with respect to y times dy. Right, that's just expanding it out. So our q dots sort of cancel. But we can't cancel out dx or dy, right? Because we have dq, dx, dx, and dq, dy, dy. So there's nothing to cancel there. So those have to kind of carry along. So let's write it out. This looks in simplified form just like this, dq dot x dx dx plus dq dot y dy dy equals 0, right? That's our differential equation, partial differential equation in terms of heat flow. So now is when we would say, all right, Fourier's law, let's plug that in for q dot. So we could do that. What does that look like? So here we have partial with respect to x of Fourier's law in x. So actually we need the entire Fourier's law, but as you'll see, right, if you take the partial in the x direction, the y and the z go away, right? We're only concerned with the x direction because it's a partial in the x. So what you end up with is minus k times the cross-sectional area. So here that's going to be, say W is into the page. Let's see, so heat flow in x, I'll do it this way. Heat flow in this direction, we need to look at what area we have available to us. So let's say W is into the page. The other area that's available is like dy, right? So you get this kind of plane that's forming. So this is W times dy times partial t with respect to x. And don't forget the dx out here. Okay, so that's the first term. Then the second term is really similar. It is partial with respect to y minus k, W into the page. And now, again, we're looking at heat flow vertically this way. So I have W into the page, and then I have this sort of segment here, right? So this is W times dx times partial t with respect to y. Don't forget the dy out here. Equals 0. So fortunately, I guess there's some stuff we can do to make it a little bit simpler. So let's see, minus k, that cancels out. W cancels out. What about the dy and dx now? So dy, is dy related or functionally dependent on the partial with respect to x? No. So it's constant with respect to that partial, meaning it can come out. Right, so dy can actually come out. Same with dx, it can come out. So now we have actually dx dy on both terms, multiplying both terms. So those will fully cancel out. So dy, dx, dy, dx. So what we're ending up with here is this PDE, d squared t dx squared, this is partial squared t partial y squared is equal to 0. This is our PDE in terms of temperature. So I don't know how to solve this. Well, I do, but you don't. Don't feel bad. Take 564, you can learn how to solve it. So you could solve this, but it's kind of beyond the scope of the class. What we're going to do instead is we're going to say, let's model this as a numerical problem. We're going to use this governing differential equation to help us kind of formulate the energy balance and then solve the problem that way. All right? So there are techniques, like I said, but it's like separation of variables. There's Laplace techniques that you can use. There's some more kind of fancy stuff that is just beyond what we're going to talk about. So any questions on this analytical part?
Why do dx and dy get canceled out?
Right, so the question is, why do dx and dy get canceled out? So these in here,
No, I did not say.
because once you take dy out here, you have dx times dy. And once you take dx out here, you have dx times dy. So you have the same dx dy that cancels out in both places. Good question. Okay.
So this was all to say that the analytical approach is not going to work?
Yeah, I mean, this is all to say that, the question was, this is all to say that the analytical approach won't work. Yes, and yes to an extent. I mean, so you can, we could go through and do separation of variables, right, and make the assumption that the equation follows a certain form, go through about 4 pages of derivations, and end up with a solution, right? For the purposes of this class, I just want to show you that this is what's governing the problem, and then we can take the numerical solutions and still get an answer, even without going any further on this. So like, would I ask you to do this in a test? No, I wouldn't. But you should know it exists.